Isaac Newton was a student at Cambridge University, not a particularly good one, surprisingly, when a pandemic hit. And much like our recent pandemic, Cambridge closed and Newton had to go home. And so he went home and he started thinking about stuff. Particularly, he thought about the gradient of curves. This was something that wasn't understood well at the time. The great Greek mathematicians were excellent at gradient when it came to things like triangles, straight line shapes. But a curve is a different ball game, and they never understood it. So Newton worked it out. He worked it out from first principles, and that is on our syllabus. So I'm not going to put a full mathematical backbone into this. I'm just going to say Newton derived this formula here, and we are going to use it. The formula basically comes down to rise. This is two y values here, divided by run. But you don't need to know that. You just need to apply it. So this formula is saying, if you have y equals f of x, that's any function at all, if you want to know what the gradient function is, which is either of these two notations, then here's the formula. So let's apply it to this equation here. It's actually hard to think of equations that can be done from first principles in exam conditions. I think it's very likely to be something pretty simple like this. So what I've done is taken this formula for when f of x is equal to x squared plus 5. So this f of x plus h means take x plus h and shove it into this formula. And so I've done that here. X plus h squared plus 5. And then this f of x is literally the formula. Subtract f of x. Notice the brackets, because I've got to be careful about this sign here. Over h. And then Newton said, right, the gradient, the gradient function is this when h becomes 0. Now, what he's really saying is it approaches 0, but it gets so close to 0 that there's no difference. So you should be saying, wait a second, you're not allowed to divide by 0, so we mustn't. So you must always simplify first. Okay, so I'm following the absolute mantra. Get rid of brackets, get rid of fractions. And I've got rid of brackets. And now look, I've got an x squared here and a negative x squared. This will always be the case. You'll be able to simplify. I've got a plus 5 and a minus 5. Nice. And now I've got a fraction that has an h everywhere, so I can simplify that. And now we've reached the end, because what this is saying is that h is getting closer and closer and closer to 0. But 2x is just a normal x value. Maybe x is 5, maybe x is 3. It's just a number. And h, therefore, is becoming irrelevant. And whatever level of accuracy you want, let's say I want 1,000,000 decimal places. Well, I'll make h smaller than that. And it means that once you've got it set up like this, you can simply say this is equal to 2x. Okay, so if f of x is x squared plus 5, then we have proven from first principles that the gradient function dy by dx is equal to 2x. That's it.